One of the biggest hurdles in moving multimodal large language models from offline video analysis to real-time streaming is the linear explosion of visual tokens. In a streaming scenario, the video is theoretically infinite. If you try to feed every frame into a model, you hit a wall. Either you run out of GPU memory and trigger an OOM error, or you use a naive truncation strategy that causes the model to suffer from catastrophic forgetting. Most current solutions rely on uniform sampling, just taking every nth frame, or low-level metrics like optical flow. But these methods are often blind to actual semantic meaning. They might keep a high-resolution frame of a static wall just because it was the scheduled frame, while discarding the exact millisecond a critical action occurs. This is where CurveStream comes in. CurveStream is a training-free, curvature-aware hierarchical visual memory management framework designed to solve this exact problem. The core insight behind CurveStream is geometric. The researchers observed that if you map a continuous video stream as a trajectory within a latent feature space, the regions with high curvature, the sharp turns in that trajectory, align almost perfectly with critical global semantic transitions. Think of it this way. If a camera is panning smoothly across a room, the feature trajectory is relatively straight. But the moment a new object enters the frame or a sudden action occurs, the trajectory takes a sharp turn. By measuring this curvature, the system can geometrically identify the most valuable moments in a stream, ignoring local noise and smooth camera movements while pinpointing the exact boundaries of new events. To implement this, CurveStream uses two primary modules, the Curvature-Aware Scorer, or CAS, and the Hierarchical Visual Memory Management System, known as HVMM. First, the CAS module extracts global feature representations using a frozen visual encoder, like DINAV2. It then calculates a curvature score based on two things: first-order motion variation, essentially the difference between consecutive frames, and second-order geometric curvature. This second-order metric is the key. It measures the angular deviation between feature displacement vectors. When the direction of feature evolution changes abruptly, the curvature score spikes, signaling a high-value semantic transition. But a static threshold for these spikes wouldn't work, because different videos have different pacing. A fast-paced action scene has a different baseline curvature than a slow-moving documentary. To handle this, the HVMM module uses an online K-sigma rule. It tracks the running mean and variance of the curvature scores using an exponential moving average. This allows the system to generate dynamic admission thresholds that adapt to the video in real time. Based on these thresholds, incoming frames are routed into three hierarchical states. First, there is clear memory. If a frame's curvature score exceeds the high threshold, it's flagged as a significant semantic shift. These frames are kept at their original high resolution to ensure the model has the fine-grained detail needed for reasoning. Second, there is blurred memory. Frames that fall between the low and high thresholds are considered intermediate transitions. To save on the token budget, these are downsampled to a minimal resolution, typically 224 pixels, preserving the causal chain of events without bloating the memory. Finally, there is the discard state. If a frame's curvature is below the lowest threshold, it's deemed redundant and is dropped entirely. To keep the memory footprint constant and avoid OOM errors, the system uses a strict first-in first-out eviction policy. Once the memory bank hits its maximum capacity, the oldest tokens are removed to make room for new ones. The results of this approach are impressive. In testing across benchmarks like Streaming Bench and OVO Bench, CurveStream consistently delivered absolute performance gains of over 10% over its baselines. When integrated into the QN2, 5VL7B model, it achieved accuracies of 84% on Streaming Bench and over 73% on OVO Bench. Perhaps most notably, this framework allowed 7B parameter open-source models to consistently outperform closed-source commercial systems like GPT-4o and Gemini 1.5 Pro in these specific streaming tasks. The researchers also conducted ablation studies to see if the components worked independently. They found that while the CAS module improves semantic perception and the HVMM module helps alleviate forgetting, the two together create a nonlinear synergistic effect. The CAS identifies the what and when of a semantic shift, and the HVMM provides the architectural where to store it efficiently. Because CurveStream is training-free and model-agnostic, it acts as a plug-and-play module. It has shown strong scalability across different model sizes, from 4B to 32B parameters, without requiring tedious hyperparameter tuning. By treating video memory not as a simple queue, but as a dynamic, geometrically guided trajectory, CurveStream provides a robust path toward real-time, long-term video understanding, opening the door for more advanced applications in embodied AI and autonomous robotics.